Okay, now we've figured out syndrome measurement as well as the recovery, which is actually the diagnosis, and then the fix to try to remove the error. Okay, but you see that in my earlier discussion, we have derived these particular syndrome outcomes by talking about what happens if you have no error or just one error on a single qubit. This was where I had x1, x2, or x3. The question now is, in fact, what happens if the bit flip occurs on two or more of the physical qubits? Remember, right at the beginning of the lecture, we had talked about the cases that you can have 2 or 3 bit flip happening, right? These occur with lower probability. You have 2 errors with probability that's of order p squared. You have 3 errors with probability p cubed, right? But they nevertheless still happen, and it's useful to see what really happens with those situations when I try to do my syndrome measurement and recovery in this particular manner as detailed by the table. Okay, so what happens with 2 or 3 bit flip errors? Okay, so it's easier to explain this just by looking at a particular situation. So suppose that I have 2 of my qubits suffering from the bit flip errors, and suppose that's a particular 2 bit flip errors that occurred is x1, x2. Okay, so this just means that qubit 3 is okay, it didn't suffer a bit flip, but the first qubit and the second qubit both had bit flip errors. Okay, now remember that I come back to thinking about my 0L and 1L state. So my 0L state is this state 0, 0, 0, and then my 1L state is 1, 1, 1. Okay, and then my general logical state is some linear combination of these two things together. Okay, now if x1 and x2 occurred, this state in fact becomes the state 1, 1, 0. Okay, this state becomes the state 0, 0, 1. Yeah. Now, once I have these states, I now do my syndrome measurement on these states. Let's see what are the outcomes we are in fact going to get. I'm going to ask 1 and 2 qubits having the same state. I look at this, 1 and 2 qubits are at the same state. So the answer to that is yes. So if I'm measuring Z1, Z2, which asks whether or not 1 and 2 qubits are the same, Z1, Z2, I'm going to get yes, which is a +1. Okay. Now I ask my second question, are qubits 2 and 3 the same? We find that no, qubits 2 and qubits 3 are different. So my Z2, Z3 measurement is now -1. Okay, so that's a no. Yeah. And I come back to this table, I have +1 and then I -1. That actually reads off the second row. So this tells me that the diagnosis is in fact an x3 error. Okay, and then the x3 error with the recovery operation will again be another x3. Okay, so altogether, if I put this all together, what it means is that this is the error that actually occurred that arises from the noise. Okay, later on, I'm going to do a recovery operation because of my syndrome measurement and the diagnosis and then the recovery operation that I do. I'm going to do a recovery operation that is x3. Okay, so the overall operation that gets applied to my state is in fact x1, x2, and then x3. Yeah, x1, x2, x3. Okay, which you may recall right at the beginning of the lecture when we talked about the code itself and talked about logical operators. This is in fact the logical X operator, which I've written as X bar. Yeah, what this means is that this is now a logical operator that flips 0L to 1L. Okay, the logical state 0 gets flipped to the logical state 1, and vice versa. 1 gets flipped to 0. That's what this X bar actually does. Okay, What this means is that if I had started out with this particular linear combination of my logical state, okay, after my syndrome measurement, and I had noise initially, and then as my syndrome measurement as the recovery, what you wind up with is not this state anymore, but I have this logical X being applied to it. I get this particular state. Okay, which I can also write if I use this X bar notation as this particular state. Okay. Now, the thing to note is that this is still nevertheless a state that is inside the code space. Okay, so I started out in the code space. The noise generally brings me out of the code space because after applying the noise, I'm a linear combination of these particular two states. And that's not in the code space. Yeah. So started in the code space, initially the noise takes me out of the code space. My syndrome measurement and recovery brings me back into the code space because now I'm back in this linear combination of 0, 1, and 1, 0L and 1L. Okay. However, I wind up, in fact, in the wrong state because I'm no longer as per psi L. I'm, in fact, having an X bar operator, a logical bit flip, having been applied to the state that I started with. Okay? So you can actually work this out for all the other combinations of two errors, okay, as well as the three qubit errors that will, in fact, happen. You can always find yourself in this situation where after the noise, syndrome measurement, and recovery, the state is back inside the code space. But once you are in this situation of 2 or 3 bit flip errors, you wind up with some non-trivial logical operator being applied to your initial logical state. No? Okay. So in this case, we will consider this as a logical error. Okay. This just simply means that you did not get back the original logical state that you started with. Instead, there's a non-trivial logical operator having been applied to this psi L state. Huh? This happens as long as you have more than the number of errors that you had assumed when drawing out this table. Okay, you will have this situation in this particular case for the cases where you have 2 or 3 bit flip errors. Okay, it's now useful to go back to the state that I have written down earlier to see really what is the effect of the syndrome measurement and the recovery operation that we have done. Earlier, what I had done was to write down the state, the code state itself, rho L, now written as a density operator, subjected to this noise, which is really just applying the same bit flip channel on every single one of your 3 physical qubits. And earlier I had already written down the different terms that you get inside this, corresponding to this one is a no error case. Yeah. Okay, this is the line with 1 error. This has 2 errors. Okay, so all the p square, and then this is the one with 3 errors. Okay. Now, our recovery operation had done the following. If you refer back to the table that we had earlier, for the no error situation, I don't do any operation. Okay, so this term remains as itself. The 1 error situation, these in fact, after you diagnose the errors and you apply the recovery, you are in fact removing the x1 operator, you're removing the x2 operators, and removing the x3 operators. Okay, so after the recovery, this itself, each of the terms inside, in fact, becomes rho L. Okay, each of the terms becomes rho L because I reversed the error operators. We are using the correct recovery operation, but then there are 3 of them. Yeah. Okay, so I get a factor of 3 here. Now, we worked through what happens with the situation when you have 2 bit flip errors, in particular the case where you have x1, x2 errors. Okay, we saw that this, in fact, after the recovery operation, becomes x bar rho L x bar. Okay, and in fact, you can go through the entire thing for yourself and show that following the table that we had earlier that maps you from the syndrome measurement result to the recovery operation, the combination of having two errors together with the recovery operation always gives you this x bar rho L x bar as the consequence. Okay, so each of these terms again becomes this. Yeah, so again we gain a factor of 3. Okay. This last situation where you have 3 errors, in fact this operator is already x bar. Okay. So when you in fact write down and look at what happens with the syndrome measurement, you will find that it's going to tell you that there's no error. Okay, this is again something you can work as a little exercise for yourself. So this, after the recovery, after the noise and after the recovery, this becomes really just the term x bar rho L x bar, just like this particular situation again. Huh? Okay, so now I add one more thing, which is really after my syndrome measurement. Okay, and recovery. I have in fact the following state that is left. I have 1 minus p cubed plus the 3 and then this p times the 1 minus p squared. Okay, this becomes just a state rho L. Okay, because these cases were already fixed by the recovery operation. And then what I have in the remaining two terms, all of these becomes the state x bar rho L x bar. Okay, I just need to make sure that I have the correct factors of 3 put in. 1 minus p plus p cubed x bar rho L x bar. Okay. Now, I emphasize again that this entire state is now still inside the code space. Okay, because this rho L is inside the code space. The x bar is a logical operator that keeps you within the code space. Okay, so the entire thing is now within the code space. Yeah, but if you compare to what has happened here, you see that earlier I had these p terms that were in fact errors. Okay, now these are fixed to not having errors anymore. So my final so-called perfect state occurs now with an order 1 probability and then an order p probability. Okay, the situation that doesn't get fixed are now higher order in p. I have p squared term and the p cubed term. So if I go back to compare with the situation where I have no error correction, okay, where I'm simply just carrying the state psi L now just as a single physical state. I have just psi, okay, which I now write as rho. So this is now 1 qubit only. Yeah, okay, the same state as the one that was encoded into the logical qubit. If I had this, if I go through the noise, what I actually have is the following. I'm now applying E bit flip to this row. Okay, I have simply, if you record the map here, I will have simply 1 minus P of rho plus probability P. I have a X rho X. Okay, and there's nothing I can do here because I didn't do any error correction, I didn't introduce any redundancy. This particular noise state, this is what I have. There's no way for me to fix this. Okay, so I've gone from the situation where if I had no error correction, no redundancy, my state has a bit flip error with probability P, to the situation where I did introduce redundancy and do some syndrome measurement and recovery, where now my bit flip probability, which is this case, is no longer of order P, but in fact order P squared and order P cubed. Yeah, okay. So this is the purpose of the error correction. You're really talking about decreasing the probability, in this case by 1 order of P, decreasing the probability that your logical state itself has a bit flip error.